Welcome to week 2 of the course on Bayes' rule. So this week I want to slowly go over Bayes' rule and something called decision trees. Bayes' probabilities are used to help us make decisions. And I will just go over the problem specifications. I won't I won't go over the full details of the solutions there, but you'll see them on the slides, and it'll be something that you can work through yourself in your own time. Okay, so Bayes' rule. And again, I'm taking some applications out of the AIQ book that goes with the course. So Bayesian artificial intelligence, and there's just been an incredible explosion in applications. I'm sure you can all think of a million applications of Bayes' rule, from Google Translate to Amazon Alexa to driverless cars, etc., etc. And if you've read the AIQ book, you realize that Bayes is really the foundational tool that solves all these problems. And as I said in the first lecture, one of my favorite pioneers of Bayes and AI is somebody called Claude Shannon. And there's a hyperlink here to Theseus the mouse, which sort of a mouse he developed that could solve the maze problem. So interesting historical link for you. So what does AI really mean? Think of an algorithm, and thinking of stringing together a sequence of algorithms to do something quite incredible. So think Google as the world's greatest company that does such things. And one thing that's interesting to realize, why did Bayes become popular in the last 20 years? 25 years, while algorithms really deal with the probabilities rather than certainties. And there's a question of how do these algorithms know what instructions to follow? So when you're building an AI to do something, probability and Bayes rule is sort of central to it. Now, one of the chapters in the AIQ book deals with Abraham Wald. It's one of my favorite chapters. He worked on aircraft survivability in World War II, and as the planes returned, they would look at the type of damage that had happened to the planes, and they would try and figure out how to reinforce the planes. So, for example, 60 planes were shot down, 316 planes returned, and you could see where the damage was suffered, and you can see that most of the damage was suffered on fuselage. The interesting question, of course, is you don't get to see a bunch of observations over here. So Wald came up with a very clever method for what's known as imputing missing data, or essentially filling in the missing blanks. And this is sort of the basis now of what's known as recommender systems. So YouTube, Netflix, Pinterest, lots of companies now have algorithms to provide suggestions for you over and above just you searching for things. So essentially, Wald was one of the pioneers of these types of methods. And again, we talked about Bayes' rule last week, and one of the important things to learn was I've got to get the right conditional probability. So, for example, I can just directly look here, right? I can go the 105 proportioned over the 316, and I can see probability of damage on fuselage given return safely is 32%. But that's not really what I want, right? I'd really want to see it in this box here. So I want the conditioning the other way round. I want probability to return safely given damage on engine, cockpit, fuselage, because I want to understand what needs to be reinforced, for example, or how to understand aircraft survivability. So two completely different things. Now, if you go to the web, you can read Wald's original paper. So a method for reconstructing the full table, a very clever way of estimating, of filling in those missing blanks. And now we can actually calculate the probabilities that we want. So now the probability of return safely given damage on the fuselage So we've got the 105 and we've got the 8. So again, just like last week, we just reproportion the probabilities. Is actually 93%. It's really the engine that's the problem. Maybe not surprisingly, the planes could still make it home even though they're damaged on the fuselage, but once they're damaged on the engine, could not be. Then you've got the 29 and 31. So when you reproportion, you only get to 48%. So rather than adding extra reinforcements to fuselages, adding it around engines made more sense. So I think that Abraham Wald data really shows the power of Bayesian methods, that typically it's not the conditional probability you think you want. Probability, what you really want is something like probability of return safely given damage on fuselage, not probability of damage on fuselage given return safely. Another reason why Bayes' rule became popular with all this internet analytics is conditional probability lets you personalize things. Amazon in the early 1990s came up with something called Book Matcher. Given the history of books that you've bought, what's the probability you'll buy another sequence of books? So again, recommender systems on Amazon was really one of the first ones to do these things. And so personalization runs on conditional probabilities. And with the advent of massive data sets, with recording all these transactions, you can get very good answers to these things. And again, really, it's sort of suggestions versus search, right? You as a human have to figure out what you want to search for. Lots of these Bayesian methods are actually providing you suggestions of things you might want to buy or might want to look at, right? So very quickly, what would a modern day version of the Wald example be? Would be, how does Netflix give recommendations? So again, Netflix would build up all these tables. What's the chance that you'd like a movie like Saving Private Ryan, given that you like Band of Brothers? If I believe my little matrix up here, 80%. Now the real Netflix problem, and all these problems are complicated because of the incredible scale. So huge numbers of users, huge numbers of movies, and again, remember, just like the Wald example, there's lots of missing question marks. You've got to recommend a movie to somebody who hasn't seen the movie before, so in some sense you've got very sparse data, and then no one's history is exactly like yours, right? The old way of doing it would be something called collaborative filtering. I'd find somebody that had bought a set of books very similar to me, and I would see which books that they bought that I hadn't bought, and I would provide recommendations that way. The solution to all of these three approaches is really this sort of careful modeling. And if you dive a little bit more deeply into these recommender systems, it's a huge business. As I said, YouTube, most companies have some form of recommender system. Team of people working on things. In some sense, you're trying to figure out predicted rating as in some overall average, some film offset, some user offset, and some user film interaction. And modern day versions of this would take into account nonlinearities, and by week 10 we'll learn a little bit about deep learning. So a big business doing recommender systems and finding those what's known as latent features for a person. So finding out back here what these offsets and interaction terms, what do they depend on, is really key. And with bigger and bigger data sets, better and better and better. So trying to find out exactly what are the features of the films that will personalize those conditional probabilities to you. And as I said, in most of these things, the hidden features tell the story. Oh, and again, just a quick aside, how does Netflix use that to make decisions? Well, I think a lot of their incredibly popular shows over the last 5-10 years of just their incredible knowledge of what people want in these shows. So they also use it to design shows as well. So that's sort of another offshoot of how they were able to become so successful making these shows. Okay, so another big field, and I think another growing field is medical diagnosis. partly due to the advent of genetics, so cancer diagnostics, cancer genetics. And he would sort of be a very typical example where Bayes' rule would provide an answer for you. Suppose Alice is a 40-year-old woman, and she wants to assess the chance of her having breast cancer, and she takes a mammography test. And there's an interesting, if you go to the web, I think NPR has an interesting discussion of how the mammography test was originally found, and it was very empirical. It was a very AI-based approach where people had just looked at images and matched up and said, okay, there was really not a lot of theory that went behind it, more just a big empirical data set and pattern matching. And a typical type problem would be, given a positive mammogram test, what's the probability of you having cancer? Or given a positive genetic marker like a BICA1 gene, what's the probability you have cancer? And all of these tests, again, if you go to the web, will have there's something called sensitivity and specificity of a test, or detection rate and false positive rate. All these things will be up on the web. And again, you need to know underlying base rate, what's known as prior probabilities, and then you put it all together with Bayes' rule and you work out a posterior probability. Again, if you read AIQ, I think there's a very nice discussion of this in AIQ. If you don't want to go the math route, you can go the route of imagining 1,000 cases and then cutting up the different boxes. What proportion are healthy? One interesting thing about tests is that they can have false positives. What proportion get cleared? What proportion actually have breast cancer? How many are actually detected? And how many are actually missed? So another way of thinking of, imagine 1,000 people and cutting it up. Bayes' rule is everywhere. Lots of popular TV programs even have Bayes' rule sitting there at the top. People talk about Bayes' rule all the time. And again, if I go back to that little graphical plot, you'll see that you can read off. It's basically the 8 over 8 plus 100. So conditional on a positive mammogram test. So we know we're in this little box. What proportion have cancer? 8 of them do. So we know it would be 7.4%. And sometimes that surprises people. Remember that we started at 1%. There was a 1% prior probability. I get to see a positive test. It doesn't go up to 100%. It only goes up to 7.4%. So there's still, 92.6% left over. So another thing to realize with these testing problems. Okay, another chapter in the AIQ book. One of, again, a very famous story. How do you use Bayesian methods to find hidden objects? So it's a famous story from the USS Scorpion, which you can read on Wikipedia. Somebody called John Craven found a lost submarine that was on the bottom of the ocean floor, and he used these probability maps to search the ocean floor. And again, modern day applications of this are related to more driverless car applications, GPS, something called simultaneous localization mapping. And again, you can read in detail about it in the AIQ book. So the story of the Scorpion is very interesting. Despite very long odds, they basically built these probability maps and then very logically searched through. So again, I reference you to the book to read the exact details. One person I was lucky enough to meet, there's somebody called Larry Stone, who runs a company called Metron. And if you want to read more about these types of methods, Larry has a paper in one of the lead statistical journals called Statistical Science, where he talks about how to develop these probability maps. And maybe you remember the Air France flight that unfortunately I think was going from Rio de Janeiro back to Paris. And 2 hours into the flight, I think, went into the Atlantic Ocean. and the Brazilian Navy spent 2 years searching for it, and the US Navy, Larry Stone's group, found it in about 2 weeks using these Bayesian probability maps. Another friend of mine, actually Neil Gordon, has written a book on what is known about MH370 as well. So if you want to know more about that, read there as well. Okay, so there's this big area of Bayesian search. As I said, modern day applications are really sort of Tesla, Google Waymo, are more the driverless car approaches. You create probability maps for your search grid. You start with a location with highest prior probability and work on from there. And Bayes' rule is all about updating prior beliefs with facts to give you revised beliefs. So an interesting class of problems. Okay, let me just drop back and talk a little bit about these testing examples and give you a few more definitions. So disease testing, or any kind of I'm going to do a big catastrophe modeling example. We'll see things in a decision tree format. So this is another way of thinking about Bayes' rule. So suppose you've got a 2% chance of having a disease, 98% chance of not. Suppose you take a test that can identify that with 95% probability and not with 5, and then 0.01 and 0.99. If you get a positive result, so given you've tested positive, what's the chance you have the disease? And so again, you can put them into tables, and again, you can do a Bayes' rule calculation. So given, remember how I like to go from these joint probability tables, given that t equals 1, so I'm in this box, I essentially just have to reproportion the 0.019 probability. So I have a 2% chance to begin with of having the disease. That's probability that d equals 1. I test positive. I've now got a 66% chance of having the disease under these assumptions. Again, if you don't think in terms of Bayes' rule or probability tables, you could look at 10,000 people, or here I've looked at 100,000, and you can just proportion people according to their percentages. And again, if you do the math correct, you get exactly the same answer. You'd still get a 66% chance, and so there's still a 1 in 3 chance of you not having the disease. And again, you'd have to have a second test of an independent test that would, this again would then go into Bayes' rule, and you would see if you would test positive again on a second independent test or independent method. So, nothing is, you learn pretty quickly that with Bayes' rule, nothing is certain, but you're doing your best to assess what the probabilities are at each stage. So 2 concepts again. If you go to Wikipedia, you'll see definitions of these things: sensitivity of a test, specificity of a test. What's the probability of you correctly identifying people, right? So in a perfect world, you'd like this to be equal to 1, or the probability of not t given d to be approximately 0. And what's the specificity test? The true negative rate. So the probability of not t given not d. And again, they're related to what's known as false negative and false positive rates, or again in statistical terms, they're related to type 1 and type 2 errors. And the goal in all of these things is to find what's the probability you have the disease given you've tested positive. And as I've said before, any modern day genetic test or any test, you'll be able to go to the web and you'll be able to see what sensitivity and specificity are of these tests. Okay. Excuse me. One other thing you see a lot is something called a confusion matrix, which is basically just plotting accuracies and errors. So given an empirical data set and given a method, can you actually go in and work out this confusion matrix. So again, something to look at. Okay, another class of problems. I'm just giving you a very quick sequence of problems. Is something called a Bayes classifier, and this is a hyperlink. So Silicon Valley. If you haven't seen the Not Hot Dog sketch on Silicon Valley, please click on the link. It's a great example of a Bayesian classifier. A standard machine learning problem is I have some input X and some output Y. So if I have an image of a cat, I would like to identify a cat. Or if I have an image, I'd like to identify hot dog, not hot dog. And again, people build these Bayesian classifiers. And again, how do you classify something? You look up in your Bayes matrix and you say, okay, or your Bayes conditional matrix, and you say, okay, what value gives me the largest possible posterior probability? So Bayes classifiers. Here's an example for you to do. I won't go over the math. I'll just flick through the slides so you can see what a typical Bayes rule question would look like. You're developing a new product. You want to test market it. Based on positive, neutral, negative reactions, what's the chance of high or low sales? And again, in all of these Bayes problems, you have to start off with base rates or priors. You have to start off with a sequence of conditional probabilities. I like to put them into notation. So step 1, high sales or low sales, positive, neutral, or negative response. And again, from that list of probabilities, I have to write out what my conditional probabilities are. And again, I have to write out what my base rates are. So, look after class and see if you can put all these numbers together. What do I really want? I want to know what's the chance of high sales given a positive response. And I want to use Bayes rule to do this, right? So I want to say this is probability of positive given H, probability of H, all over probability of positive. And so I start by working out the denominator, something called the law of total probability. Turns out it's 19.4%. I then plug all my numbers into Bayes rule, and out comes my answer. Excuse me. I get my 28.8% answer. And remember that, again, sometimes this does confuse people, right? And nothing is really certain. I've learned new information. All I do is I update my probabilities. So I started with P of H at 8%. I've got a positive pilot test. Now I know that my posterior probability, as it's called, is 28.8. Here's another example out of the AIQ book. It's a little probability model for Warren Buffett. Can you identify the two-headed coin? So again, there's lots of anomaly detection problems in Bayes. And so, can you identify somebody who's really good at investing, for example? So just imagine this sort of problem. I've got a large jar with just over 1,000 coins. I've picked it so the math gives me 2 to the power 10. And I know I've got one double-headed coin. So if I always toss a double-headed coin, I always get a head. And I see 10 heads in a row. So I pick one coin at random. I don't know whether it's fair or you don't know whether it's fair or double-headed. You flip it 10 times and you get all heads. Of course, the second you see a tail, you know it's not a double-headed coin, but I tossed it 10 times, I get all heads. What's the probability you really do have the two-headed coin in, or I do really have the two-headed coin in my hand? And again, if you just sort of logically think, you think it's something close to a 50-50 bet. Well, take a little bit of time and see if you can figure out what's on the next slide. Here's my Bayes rule calculation for it. And essentially, we get to the 50-50. So, 10 years, let's say, of beating the S&P index. What's the odds I found that manager or that person that really is the double-headed coin that will keep on keeping on beating forever is, it's not 100%. It's up there at 50%, and I started off at a much lower probability. As I said, there's a million examples of Bayes rule. the Apple Watch has gotten smarter and smarter at telling me things about my health. What would be a Bayesian application for the Apple Watch? Can it identify if I'm having an atrial fibrillation? Can I tell me something? Again, if you click on the link, there's a hyperlink. We're up at 66% probability. So if the Apple Watch warns you that you're having a heart attack, maybe there's a 2/3 chance that you're having it. And on the other side of the coin, remember there's a 1/3 chance that you're not. And there's been examples of people turning up to the emergency room at hospitals getting very worried. And of course, a certain percentage. So from the perspective of you working in an emergency room, you tend to see a lot of these false positives. Remember that no test can really be positive. Another favorite old problem is called the Monty Hall problem. Do I switch doors? There's 3 doors. Behind one door is a car. The other 2 doors had a goat. You get to pick a door, so you pick door A. Monty then reveals one of the doors that doesn't have the car or the goat, or the goat. Maybe he reveals door B. So you're left with two possibilities, A or C. And to the human mind, it looks as if there's only 2 doors left. And so you think, oh, shouldn't the odds be 50-50? Everything's random, and he's just opened up a door that doesn't have the goat. Well, it's not quite as simple as that. You start with initial probability of 1/3, and if you go through the Bayesian math carefully, it's still 1/3. Or another way of saying that is that the odds that it's behind door C is 2/3, which is bigger than 1/3. So in theory, you should switch. But there's a human bias that I've already picked door A, and people not that keen to switch. But Monty Hall problem is a good example where you have to be very careful about specifying your conditional probabilities. And he gave you the option to switch, and you really should switch. Okay, so here's the last example of this week of Bayesian. And again, as I said before, you should be checking that you can go through these Bayesian calculations. Another huge area is putting things into a decision tree format. So nodes in a decision tree is where you've got places of uncertainty where you get to make a decision, and boxes or branches you get to put probabilities down on each branch. And I once worked at Swiss Re for a while, and these big insurance companies have teams of people that look at these decision tree type models to try and figure out odds of catastrophes. And in the age of climate change, some interesting problems arise, right? And again, I won't go over the full details. I'll leave them for you, but you'll see what a typical decision tree would look like. So you live in a place that's prone to mudslides. A mudslide would cause you a lot of damage. You have an option to build a wall, and you also have an option before you spend the $40,000 to build a wall to get an opinion of a geologist. And so there's a couple of questions that come to mind, right, in these situations. Should you build a wall, and should you use a geologist test and Bayes-Roll? And of course, you know that given that I like Bayes-Roll, I'm going to try and persuade you that geology test and Bayes-Roll is a good solution. And what we're aiming for here at the end of the day is just really a matrix that gives you expected cost together with the associated probabilities. So there's going to be no one. It sort of depends on your risk return preferences. So there's no one unique answer, but at least you want to figure out in the different branches what makes sense and what doesn't. So we're going to formally solve this by building a decision tree. We're going to look at expected costs of going down each branch, and we're going to try and figure out whether the geologist test makes sense. So writing things out in a decision tree, everything's in thousands. So here, down here, I'm going to lose $1 million. Here I'm going to lose 1,040,000 because I've actually built the wall going down that branch. And I can, in theory, work out all the conditional probabilities going down my tree, right? So, if I don't build the wall and the slide comes with probability 1%, my expected cost of this branch here is $10,000, right? 1% of the $1 million. And 99 times out of 100, I'm totally fine. Okay, so that's what a decision tree would look like. If I want to convert it into a Bayes rule problem, I need to know the sensitivity and specificity for the geologist. So I need to know some historical data on his probabilities and his tests of assessing things. So the probability of test positive given slide. So if you look historically, he'd have to tell you that's, say, about 90%, and probability of not test positive given no slide is 85%. So remember, there's always a sensitivity, specificity, false positives, false negatives buried in there. Let's set up Bayes rule. I've got my initial prior probabilities. I've got my lower total probability. So this is this is from the geologist's perspective. Of all the times he's made an assessment, how often does his test come out positive? Only about 1 time in 6. So you pay $3,000 to the geologist. 5 times out of 6, he'll say nothing. 1 time out of 6, he'll say that you've got a possible problem. Now, if the geologist says nothing to you, remember that's information. So again, you're trying to find your optimum course of action. So any information from the geologist is worth something. It's just a question of figuring out how much really is it worth to you. And in order to do that, you need to use Bayes' rule. So let's just do a simple one. What's the probability of slide given test positive? Again, I'm leaving you to put the numbers in. Now it's 0.0571%. And remember, you started at 0.1. So you started at a 1% chance. The geologist tells you that, oh, you've maybe got a problem. Well, it's only 5.7%. So, even though the geologist has tested positive, 94.3% of the time, the slide's not going to happen. And remember that the value in the geologist is just telling you that the risk-return characteristics have changed, right? Similarly, slide given not positive, that's now 0.1% of a chance, right? So you've gone from 1% all the way down to 0.1% of chance, so that's good news for you. And then, putting it into economic costs, should you build the wall or not? So let's just first of all do that underlying base rate. What's the probability of losing everything given build without testing? It's given by this probability that's sitting down here. Okay. Different paths that you can go down. So one path is test positive. We worked out that probability. If it tests positive, you're going to build the wall. There would have been no point paying the geologist $3,000 if you were just deciding, I'm just, just not going to build the wall totally. Then I need to work out that posterior probability of slide given test positive, and then I need to work out that probability that the wall doesn't hold, right? Remember that the wall only held with 95% probability. So that 0.05 came in here as well. So that's one sequence. Another sequence is it tests negative. I don't build again. If my risk characteristics were, clearly I'm in the no build case. Slide given negative was equal to that, basically 0.1%. If I put those paths together, or to the top path, or to the second path, before I see the geologist, if I sum those two up, that's about 1 in 700. So I've basically provided my matrix of risk return characteristics. So I could go through life, by just not building, ignoring the building of the wall, ignoring the geologist, my risk is essentially 1 in 100. That initial prior probability that the mudslide would happen. And so my expected cost off the $1 million is 10,000. Or I can just build without testing. So I incur $40,000 cost. My expected cost from the mudslide happening and the wall not holding is way, way lower, is 1 in 2,000. But of course, I've incurred a much larger cost. Or the option that the geologist Bayes rule option, I basically have an expected cost of 10,760. Convince yourself that summing up the 3,000 for the geologist, etc., etc. My risk is not as low as build without testing, but it's way lower than not build. It's that 1 in 700. So if you look at these, look at this matrix in terms of expected cost and probabilities. I get an expected cost of just over $10,000 with a probability 1 in 700 versus the do nothing strategy of 1 in 100. Of course, if you're incredibly risk averse, you have to do box number 2. So what do you choose? A personal choice. I'm going to choose test and Bayes rule. Okay, well, thank you for listening. We've covered all our Bayes rule applications, and we've looked at Bayes rule from a perspective of decision trees.